not C, because C that did not happen. And it recognizes not C because it predicted C, but it didn't observe C. So whenever nars predicts something, then it will anticipate or expect the prediction to materialize or to happen. And this feedback can then be used for the system to find negative evidence for this hypothesis. So the system will understand that B alone does not suffice to get C. And it will see that the other hypothesis, AB, does not fail in this case. Whenever we had AB, it predicted C and C happened. AB and C happened. So even this case is not negative evidence for this case because there was no A. This was only a case where we had B, but we didn't have C. So this hypothesis will only have positive evidence in this sequence, while this one has some positive evidence from those examples, from this one and this one, and we will have negative. Exactly.
And whenever you revise it?
Exactly.
So you will be able to revise it, it's still the frequency and confidence could be better, bigger on the first, on the D.
Exactly. So it might be that because it has seen this pattern so often, it takes more examples for it to see that this hypothesis has less truth expectation than this one. So it depends how. So it will always track the positive and the negative evidence for each hypothesis, and dependent on how much positive evidence. In this case, there will, at least for this sequence, there will only be positive evidence, but for this hypothesis we will have both. And at some point, if this happens more often, at some point this hypothesis will win, or will have a higher truth expectation than this one. And this is important because it allows the system to have some kind of multi-step conditioning where it recognizes that a certain additional condition has to be fulfilled so that a certain event will lead to a certain consequence. This is important. So what OpenNAS does, event gets predicted. It's negative evidence. Or negative event. Now there are some challenges with this, because at what point can the system decide that C did not happen? For instance, maybe the event occurs at some point later in the future. Maybe this is not a counterexample to this hypothesis. Maybe it's just a matter of waiting longer and suddenly the event will appear as it predicted. And so how can we handle this? And there are multiple things involved here. First, what I didn't show here yet was that when the temporal relationships are formed, the system also adds timing information, like if we go back here, something like if B happens, we write it this way with what we call intervals. For instance, 5 steps later, C will occur. So we always have, when we do the temporal induction, we always add the timing information. So this B leads to C is actually something like B plus 5 seconds leads to C, which is a different hypothesis to B and 15 seconds leads to C.
Is it 10 seconds?
In the system it's currently just working seconds.
Cycles.
Exactly. But we also support to use milliseconds.
Yeah, but working cycles are just all the inferences you can do so far. That's a single working cycle.
Exactly. So it uses the inference.
So it does not necessarily catches the sequence length by the working cycle. It depends on how many evidence you collected in the back. So its number of inference per working cycle can be different. That's what I'm saying. Some of them will complete the closure. Some of them will complete positive, negative evidence.
No, this is just a count of the working cycles. Each working cycle, so it's just used as a timer, because each working cycle approximately takes the same amount of time. So it uses this the amount of inference cycles, which is different from the amount of derived.
Inference cycle is one step from whatever we have, right? One inference from whatever we have.
One combination of task and belief.
Alright, so if we have two beliefs, two tasks there, so we have 2 steps forward. I mean, 1 step forward, but in 2 tasks, correct?
I'm not sure what you mean. In each inference cycle we select one concept.
Correct.
So this measures the amount of concepts that was selected.
But the concept can be different in terms of compound, in terms of that has a bigger structure in terms of links.
It doesn't matter what it will derive, it just measures how many concepts that it selects.
Yeah, I guess here we have 2 issues. What Peter mentioned is when you reach a conclusion, you may need to spend a lot of time to collect evidence, blah, 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 blah. But we are not talking about that time. Here, the time is just between B and C. We have nothing to do with how many evidence you have collected for that conclusion. That's a different story. That's not what this 5 measures. It's a time interval between 2 events when you're making a prediction.
This is really the temporal distance between those 2 events. And one way for the system to measure the distance is to use something like a timer. And here we can either use the internal clock, which is just the amount of inference steps that happened so far, or we could use a system clock that reports the milliseconds. So in the latter case, this would mean 5 milliseconds after EC happens. So it's just some kind of clock which it uses.
And on that aspect, do we now have some evidence to show the difference between those 2 approaches? I mean, using internal cycle as an internal clock, and another one just use a system clock. Some people, of course, will say system clock is much more accurate, but very often accuracy doesn't necessarily mean something what we want. Right? The first approach, use the internal cycle, actually is more natural. It's kind of like our biological clock has always been used. But some people may say that's before you have a real clock outside. If you have a real clock, my question is a real clock always better than a biological internal clock?
I would say no.
Yeah, my intuitive meaning is the opposite. It's kind of like the biological internal clock is the one you should depend on, and the outside, real clock, the physical clock, is kind of like more like a tool. Yes, for some reason you want to use a tool is more accurate, but it's probably not as flexible or general as your biological clock. I'm not completely sure about the conclusion, but that's my feeling at least at the very beginning. That's why we start using this internal clock idea rather than the system clock, which is always there. I don't know whether your experiments so far have falsified my hypothesis or not.
I guess it depends on the use case.
Yeah, of course.
If example should be reproducible on multiple machines, that have different processes.
Yes. Because the subject, the biological clock is completely subjective, right? It depends on who you are, and you switch to another person, that's a different clock.
Exactly. So I guess in case one wants to show examples on different laptops, and one really wants to have deterministic output and make sure that both examples will work the same way on both machines.
And another thing which we haven't really done is I think this is more like whether you're talking about outside process which you have no control or internal process which you do have control. For internal process, my feeling is you will see that a biological clock will work better. It's kind of like, I will do this, then I will do that, and then after a while, I'm going to do the third thing. And what that after a while means, it has a meaning to you. But if you change that into, say, after 5 seconds, it's probably not good. When you're coordinating your activity within your system. I'm not absolutely sure, but that's my intuition.
I guess for own mental operations, it's better to use the internal.
Yes, that's what I mean.
Well, for external events.
Yeah, if you control some device, some machine, of course you want a clock, right? You don't want, based on your intuitive temporal feeling. That's good.
Maybe we will need both in the end, so that sensory channels will operate with a system clock, with a real-time clock, and maybe internal time measurement, like for consequences of mental operations, will maybe be better if they use the internal.
Yeah, I have the same feeling. But of course, it's better if we can support both, right? But then it will raise the issue of their translation, mapping between each other. That can be tricky.
That's true. Oh, yeah.
I think different events may have different time scope, such as if I touch the fire and I will feel painful immediately. But such as the day and the night, the alternative, they are alternative daily, and the moon will bright and fade monthly. But the nars, but the nars maybe just can record the things happening immediately, but such as the moon, the event will happen monthly, but can it record it? Can see record it? I don't know.
So how to handle events with a duration?
Yeah, it's a duration, but it's a very large time scope.
I see what you mean.
Yeah, that's actually one major consideration for this. That is to support different, you can say, is time granularity. Okay, when you're talking about robot control, that's one thing. When you're talking about history, for example, that's a completely different thing. You say these two things happen at the same time. When you read that in a history book, they may actually have say 10 years in between. But they call it the same time. That's true. That is why another reason why we don't want to use the same clock for all time measurement all the way. We use a temporal or relative description about the sequence of what is after what, and we leave that interpretation to the context. That's also related to this. So we should be able to describe things in very different time scale using the same representation. But the internal clock is relatively stable or independent to that, but it depends on which system you're talking about.
There's one very important idea, because I mentioned that those two are not the same hypothesis, because the time they predict C is different, but we still want to have some kind of way, because in the real world maybe B and C will never exactly happen with this distance in time. Maybe one time it's 5 milliseconds, maybe one time it's 6 milliseconds, or let's say, especially if it's a longer time scale, one time it's 3,226 milliseconds and the other one it's 3,198. So what we basically want to have is that if the time interval is similar, and the first thing we want to have, if the time interval is similar, the hypothesis should also be considered similar. The second thing is the penalty which we have in this time scale. For instance, if we have +5 and +15, for this time scale, those are really different. But if we have something like +100, +1,500, and we have +1,510, then they are very similar. So we want to capture, we do not only want to capture the difference in time, but also the scale of the temporal distances. And what we there were several ideas of how to get this implemented. The first thing we did was something that we called log intervals, which basically we discretized the value to something like 15 in this case, something that takes the scale into consideration, so that, for instance, +1,500 and +1,000 what is it? Basically, how to draw it? Maybe it's better to draw it. That'd be more intuitive. If this is the time difference, basically we want to have different intervals, or we want to be able to distinguish temporal distances that are small, even if they have a little variation, while if we have temporal distances that are large, then they will map to the same term. While here, if we have the same temporal distance, they will map to different terms. So something like here plus 1 and here plus 3. 1, 2, 3, 4, 5. Let's say put this one here plus 6, 7, 8, 9. And if it happens here, it would also be a plus 9. So the idea is to take the logarithmic scale into account, so that we reach a higher time tolerance on larger time scales than for small ones. But this treatment has issues. There's one issue. What if one hypothesis is close to here?
The boundary, yeah. Yeah, that's always tricky. Wherever you try to turn something kind of like a continuous measurement into a discrete, you always have the issue of where to draw the line. But you have to draw the line. So, yeah.
This is one issue with this representation. The second one is when in case that the temporal distance really matters, it's lost. Here it will be lost because they will.
Sorry, it just occurred to me. What if we don't use integer? What if we just use real number? We still do the log function. Will that solve the problem?
This is also what I'm going to talk about.
Okay, okay, sorry. Yeah.
We got rid of this issue of discretizing events by basically removing interval information in the conceptual graph. So in the conceptual graph, this would still be seen as this concept that he needs to see. And so we keep the intervals on task level, but we do not include the data at conceptual level.
Okay.
So at conceptual level, this is still be leading to C, while the different beliefs will have different timings, plus 5. Plus 15.
Just like they have different truth value and evidence base.
Exactly.
Okay.
And so instead of having a discrete interval, what we do in revision is now we just designed a function that takes the scale into account, but also the time difference to allow to revise this hypothesis with each other, but penalizing based on both the difference and the scale.
Yeah, that's probably a better solution because this time interval is not in the grammar of narcissism anyway, right? So we can say this is not conceptual level thing, it's just some internal details about the implementation of that.
Exactly.
Previously, I didn't take that approach. One reason is I still want to keep multiple copy with different time interval in between. So you'll see that to force the time interval to be discrete will make that happen. If you say, it's just a matter of degree, so everything is just a number, then it make any two things can be revised with each other.
That's true. But
So
only with only low contribution. If
yeah, of course, only low contribution.
So you're mapping all the possible differences to 0, 1. So
Sort of.
0 would be cotemporal, 1 means infinite amount of time occurs.
Sort of. Yeah, you can put it that way. It just the tricky situation is if this A event and this B event actually have two different, both quite stable temporal relation. Then we need to be careful. For example, after A happens, then after say either 3 seconds or 5 minutes, B will happen. And both are quite stable. 3 minutes, 5 seconds, both are stable. So you want both patterns. then we need to be careful about whether we our design allow that.
Okay.
If there is only one kind of like a true relation, we can use this approach to allow some noise in the. Say you don't want to be too accurate, in this kind of thing. You say after it must be exactly 5 seconds. Then you have B. If you have 6 seconds, then that's negative evidence. You don't want that. That will kind of like disqualify almost everything. The temporal pattern we observe in our daily life. So you want to allow some difference, but you don't want to allow too much. So that's the tricky part about this business. And also, you may actually have several different patterns, which the only difference is in time. But they all exist. But the thing in between will not exist. You see, that's type of thing that we need to handle here.
Right. This is like a trade-off because we still allow the difference on just on previous level. It's just on conceptual level that
Yeah.
that
Yeah.
merged into the same thing.